There you go, buddy. Santa is out of time. He has 32 houses to hit in Springfield, he's tight on time as it is, and he's spent so long optimising his naughty list that he doesn't have time to find the perfect route. But never fear, not even we're evil enough to not help Santa. We're going to use a travelling salesman problem to save the Simpsons Christmas before it becomes mathematically impossible. Today we're looking at 3 algorithms to save the magic of Christmas. Can any of them do it? Let's find out. So there comes a time in every adult's life when an annoying child asks the question, how can Santa possibly get around every single house during the night? And I don't know why they don't give us scripts on our 18th birthday to be able to answer that question, but don't worry, today I'm going to give you the answer that you can use to baffle a child so much that they never ask that question again. So, bells ready to jingle? Let's go. So, my starting point was a map of Springfield where I have painstakingly plotted the locations of residence or work. Let's face it, Simpsons hasn't exactly told us where Dr. Nick lives, so that we can figure out which route Santa needs to take. The whole process was incredibly painstaking, so I've documented how I did it in the link up here. However, I originally made this map so I could find the perfect trick-or-treating route for Bart Simpson using a combination of Dijkstra's and orienteering algorithms, so we can skip all that setup and get straight to the good stuff today. How do we use the travelling salesman problem so that Santa can complete his hit list? So if you're not familiar with the travelling salesman problem, it's a problem from the world of computer science that says that the travelling salesman, Santa in this case, must start at one particular node, traverse the whole graph, visiting every other node, and return back to the starting point. Let's just say that Santa can only move between towns at a certain point. It just keeps the maths easier if we do it this way. It's not strictly the case that the travelling salesman must visit each location exactly once. In much more complicated problems, there might not be a path connecting every single pair of nodes, and so he might have to visit some nodes twice to get around. But in our case, we've built the map so that every single character is connected to every single other character, so that makes it a bit simpler for us. Except Mo, by the way, he was broken for my trick-or-treating video, and I was going to fix him for this video, but it turns out he's on Santa's naughty list, so I don't have to. There are many ways to solve the travelling salesman problem with a variety of different algorithms, but today we're going to look at 3 and make a recommendation that will save the Simpsons Christmas. So when solving a technical problem, some people make the mistake of instantly jumping to the most complicated algorithm they could think of with all the bells and whistles, when in reality, simplicity usually wins for a number of reasons. It's easier to implement, it breaks less, and when you do get a bug, it's much easier to find out what's going on and fix it. And let me tell you, from a decade in quant and data science department, when the proverbial hits the fans, the quicker you can get in there and get it solved, the better. So with that in mind, we're going to start looking at this problem by taking the most straightforward approach, the brute force method. And we're going to start at Kent Brockman's house because I kind of already calculated this earlier for an art attack moment later on, so that's why. The most basic thing we can do is check every single path. So let's go from Kent Brockman to The Simpsons, Kent Brockman to Ned Flanders, Kent Brockman to Apu. There are 30 different options for him to choose from for his first step. Say we pick Ned Flanders. Well, we've already started from Kent Brockman, so there are only 29 places we can go to next, and wherever we pick from there, there are only 28 options from there. As I'm building this up, you can see why this problem is so hard, because if we have 30 choices for our first step, and then 29 different choices for our second step, that's already 870 different choices, and we have gone literally 2 nodes. Following this through, we get 30 factorial different possible choices, which is a number that looks like this. I thought I'd save you the pain of me trying to read that out. To give you an idea of how big this number is, the number of seconds in a million years is in the range of 10 to the power of 13. So if I set this code off running, then the universe would end before my code did, assuming it didn't crash first. One of my favourite things about data scientists is that we often come from quite theoretical, mathsy, statsy backgrounds, and so when a computer scientist comes along and tells us that this problem is in the order of n factorial, we just nod along as if we know what they're talking about. But I'm going to break the taboo today because I actually went and looked it up, so I'm going to tell you exactly what it means. It literally means the number of operations is some constant times n factorial. So as your n grows, the complexity grows with n factorial. That means we have an algorithm so computationally expensive that it's either going to blow its memory or the universe itself. Alright, so brute force will give us the best possible path, but the time it takes isn't really realistic. So in the real world, we need to make some optimizations. So let's start by seeing if we can improve on this algorithm. The biggest problem with brute force is the sheer amount of paths that we need to calculate, which takes a huge amount of time. So one thing we can do is we can reduce the number of paths, and that'll have the effect of cutting down the computation time significantly. One thing we can use is something called the Held-Karp algorithm, which makes use of dynamic programming techniques such as recursion, and that's a whole other topic for another day, so I'm not going to get into the full details, but here's what you need to know. The key idea is that we solve the larger problem by breaking it down into smaller chunks. So the main problem is, how do we find the shortest path that starts at Kent Brockman, goes around all of the other 31 Simpsons houses, and then ends back at Kent Brockman again? And we can cut this down into a smaller chunk by looking at what is the shortest path between Kent Brockman and any other final house. And then we only have to calculate the jump from the final house back to Kent Brockman at the end. Really, it's the exact same problem, we just stop one house earlier. Let's go down a few layers until we reach somewhere where the numbers are a bit more manageable. So let's say level 4. We're going to find the shortest route that starts at Kent Brockman, finishes with Mr. Burns, and passes through a specific 3 houses to get there. Once we've calculated it, we store it. That's the important part here. Now when we move up to higher layers, we never actually have to calculate the distance between Kent Brockman, finishing at Mr. Burns, passing through 3 houses. Again, we can just reuse the shortest distance we calculated earlier. That means we never have to do that calculation again. Because we're not having to calculate every single path, starting at Kent Brockman, ending at Mr. Burns, and passing through 3 houses again, we're actually cutting down the computational time significantly. This drops the total computational complexity down from order of n factorial to a much more reasonable order of n squared 2 to the power of n, while still maintaining the rigor of knowing that we have covered every single possible path. There's only one problem. That's still a lot of paths still to calculate. I mean, we are now less than the total number of seconds in a million years, but not by much. It's time to go even deeper. The reality of the travelling salesman problem is that you don't really have to have that many nodes for it to become completely computationally impractical. I haven't even considered most of the kids at Springfield here, like Nelson, Sherry and Terry, Fallout Boy, and already the problem is so big that I can't solve it before the universe ends. So like much of life, if we want to get things done, we have to compromise. One such algorithm that tips the balance towards speed at the sacrifice of some accuracy is the the greedy algorithm. It's so called, I guess, because it's the opposite of delayed gratification. It's the hedonistic pursuit of the most straightforward path in front of you, regardless of how much pain that might cause you later down the line. It's a definition of short-term pain for long-term gain, because taking the easiest path at any one point means you might be doubling back later on, and maybe even at great distances. The time savings gained by this approach are pretty hard to beat, and Santa has left it way too late in the year for something else, so he doesn't mind a bit of doubling back if he gets the route out on time. The reindeer only go out once a year anyway. To show you just how much the greedy algorithm speeds things up, I actually ran this earlier on a subset of nodes, by the way, because I don't have a million years to wait for code to run. I was playing around with different numbers of nodes to find the best version to use for the video, and when I ran with 11 nodes, it took 58 seconds to complete. When I ran with 12 nodes, that was closer to 700 seconds. That's 11.5 minutes. I didn't dare run with 13 nodes, and it's an unlucky number anyway, so. I then ran the Held-Karp algorithm, which decimated the times to 0.2 and 0.7 seconds, which is a huge time increase for 11 and 12 nodes respectively. But I'm still only running with a maximum of 12 nodes. If I ran for the whole graph, it would still be far, far too computationally intensive to run. And get this, for the greedy algorithm, I got to take the hedonistic route myself because I could use the built-in package into the graph library that I was using to approximate the greedy algorithm. Quick to code, even quicker to run. We are in millisecond territory here, and it took 0.03 seconds to run the entire 32-node graph. Speedy, right? However, what we save in time, we spend in accuracy. Both Held-Karp and brute force agreed on the optimal distance, but the greedy algorithm gave us a 1584 compared to the more accurate 1486. The 12th node saw the addition of Mr. Burns, and I really need to do some reflection as to why I keep using him as an example, but here it is quite fitting, because the greedy algorithm gave 2715 compared to the more accurate 2303 of brute force and Held-Karp. So I guess what we've learned from this is that sometimes we need to compromise. We can't always have our cake and eat it. We need to concede on certain points, like the accuracy, in order to get what we really want, which is Santa to deliver presents on time. Who said that nerds don't have social skills? Actually, I wanted to use this series to showcase just how broad data science is, because all of these algorithms that I've used sit firmly in the camp of computer science. But sometimes we have to be creative and use all of the tools in our toolkit to solve whatever weird problem our boss has dreamed up next. Oh wait, that's me now. I joke, but at Evil Works, we are living and breathing data science after years doing this for real in our previous jobs. And we have created a platform for data scientists like you to take your workflow from Held-Karp to greedy, but without the loss in accuracy. We'll be having a closed beta for our subscribers to try out next year. The information is down below. Join the waitlist and we'll give you all you need to know. I will happily info dump all of it to you. I love talking about this stuff. Otherwise, like and subscribe and tell me, what's the most hedonistic hack you pulled off in your data science projects?